All right, everyone. Thank you for coming to the Hack Night. For those of you who don't know, Hack Night, well, Hello Miami is an organization. We do Hack Nights every week at a Thursday at Moonlighter Fab Lab. What is a Hack Night, you may be asking? It's basically where a bunch of nerds get together and build cool stuff. Typically it's an engineer or a maker or like somebody who's building interesting things with technology. We all get together from like 6 p.m. till midnight, sometimes till 6 a.m. like what I was doing on Thursday, and just like build whatever projects that we're working on. I was working on this thing till 6 in the morning, but yeah, I'll talk about that a little bit later. What we're going to do a few lightning demos. At the Hack Nights, we generally do like a single lightning demo, but this is going to be jam-packed with them. Our first speaker will be Kurt over here from Hextronics. Hextronics builds drone base stations so that drones can be deployed autonomously from anywhere in the world, frankly. And he has a factory building these base stations here in Miami, out in like West Kendall. So he's going to be talking about his motor control board for the drones and for anything else that you may want to use a motor control board for. So, ready, Kurt?
Yes. Okay, we made it. Hello, Fairchild. Hello. And yeah, excited to be here for this year's Maker Faire. And I'd really like to talk about a little bit starting on Hextech, which is a circuit board that we created a little bit for ourselves, who are builders, but then also for the community of creators that we hope to inspire with our technology. And so I'm just going to touch into some of the technical components behind this circuit board and why we made it, and then I'll go a little bit more into the background of Hextronics as a company, kind of where we started from, why we're so close and tied to the Miami ecosystem, and frankly why we love making automatic drone stations. And so the main thing that powers our drone stations is a variety of different stepper motors, because we need a level of precision to accurately know where the battery is, where the drone is, and how to create that entire cycle of battery swapping into one kind of compact and reliable system. And so the circuit board here, the Hextech muscle we call it, drives 4 stepper motors with the industry's most powerful stepper drivers, as well as drives a variety of different DC, brushless DC, MOSFETs, and limit switches, all kind of tied together into one operating system that's driven by the new ESP32S3 that can host its own Wi-Fi access point, as well as tie into local Wi-Fi point to then have kind of global programming and access control. So typically how you interface with it and how we interface with it as it's installed in our own products is simply through just a serial connection, like through USB-C. And then also you can talk to it just over the cloud. It accepts MQTT and HTTPS endpoint hits. And so, yeah, I can go a little bit more into the specs, but the main reason why we went for this is because when I was making these circuit boards that drove some little robots that delivered food in restaurants, or just the early stages of our prototypes, I would constantly be fed up with this mess of just wires that connect a microprocessor to a stepper driver, to a limit switch, all this different stuff that would end up making kind of a rat's nest and eventually magic smoke that nobody really likes to have happen. And so the main concept behind that Hextech circuit board is to consolidate all of the motor driving components into one system that then makes it really easy to build whatever project that you're working on. And so the boards can be chained together in any which way, and they have an open I2C channel to access as well. So it's kind of like the easiest thing to plug and play into any design that you're working on. So here's kind of the variety of different components that this one system actuates. Essentially being able to drive a variety of the industry's most powerful stepper motors that have 2 coils for enhanced precision, and then limit switches of any kind, or even as a simple GPIO, we've got roughly 8 ports to do so. And then we can also drive DC motors, or solenoids and electromagnets, or just like a simple LED light strip. And all of this over I2C with additional PWM output controls directly from the ESP32 pinout. And from here, the main thing that I hated when kind of building the first circuit boards that we made, and why we changed to the muscle is the connectors. So the connectors that you'll notice are those little screw terminal pluggable block connectors that you don't need any soldering kit, you don't need any special crimping device. You literally just need a screwdriver and a wire, and sometimes I even peel it with my teeth, and I plug it in and screw it on. And that's how we're able to go from idea to prototype so quickly, because we kind of just shoved everything that we needed in this one board, and then, hey, we have a new idea for a different robot. Take the board, plug everything in, and then boom, you can send all the serial or HTTP commands to it to program everything in the cloud. So I love it. And let me just go a little bit back in time. I'll run through this pretty quick, but I want to go into a little bit of our history as Hextronics and me as a human. I got to zoom in pretty quick. When I was growing up here in Miami, Florida, I went to a school not too far away from here called Palmer Trinity, and that's where I started kind of being an entrepreneur. I was in a couple different courses that taught me how to really find customer needs and be able to create a solution that brought value to them. And so one thing I saw in the city of parks all throughout Palmetto Bay is it was lacking kind of public infrastructure to rent out a bike and go from park to park to park. So during my time in high school, I created this bike rental program that's currently installed at Daring Estates and is now kind of being used across the Miami or Palmetto Bay community, and was, after I graduated, got adopted by the local county government. There's the mayor, and then they even gave me a certificate for it. But then as I kind of grew into engineering, I wanted to take my kind of initial design ideas for entrepreneurship and building products into the real world, where you can make something physical that solves a problem that people just think is cool. And this is like my first invention, pretty much. It's a small little Assassin's Creed blade thing for a pencil. And from that, I continued to understand more and more about 3D printing, about making like firmware and programming these little kind of ESP32 small microprocessors that would interlace with a bunch of different motor drivers. So you'll see, like, this is the robot delivery system I was talking about, where there's these little robots that would drive on train tracks overhead. This is one that I prototyped in my apartment. And really building these first iterations was so annoying. You'll see all of the wires that are required to essentially drive motors, communicate with like an ultrasonic sensor, a bunch of different voltage dividers, microprocessors, and all of this came together in ways that basically kept me up for way too many nights, having to rebuild the same board because I made a short on my vector board somewhere, and it fried the whole system, and I had to start from scratch. And that's kind of the foundation for what got us into building our own circuit boards and really using them in production. So yeah, this is still kind of prototypes before Hextronics. And then in school, made kind of the first drone station design or concept that would swap the battery of a drone. And these were like our first circuit boards. You can see how we got a little bit deeper into actually making the board that would create the traces within, like from these voltage dividers and stepper drivers to an ESP32. But then again, it wasn't like completely integrated as one whole system. And so we continued. I graduated from school. The product continued to take more of a shape in my garage back home. So this is my garage in Homestead, Florida, where we started making our very first designs of the drone station. And then further, we got into actually making the embedded circuitry that goes into them, and you'll see the variety of different connectors we were using and kind of failing with over time with those little pesky JSTs or insulation displacement connectors. And so we got quite a few units in production at our Hex Labs, we call it, and we hired some interns from my local high school. We moved into a big warehouse and we got a large unit order. Brittany, my sister, sitting around over here, painted our first entryway insignia. And the rest is pretty much history. Don't want to take too much more of your time, but here's like the underlines of the systems that we created right before the muscle that has all of the inner like components to drive these stepper motors at maximum power. And here's my good friend Nick holding it. So this is the master control board called the Dumbledore that we basically shrunk down all of that capability into the muscle. And so yeah, that's the story.
All right, cool. Thank you, Alie, for the invite. My name is Schneur, and I run a company called EBS Studio, and we're an industrial design agency based here in Miami, Florida. We work in a couple different industries right now across consumer product goods. So we're not as engineering as Hextronics, so that's super, super cool what you guys do. We kind of do, we would say case design for tech, and then low-tech consumer products. You could think of eyewear, which I'm going to walk through a little bit today, baby products, kitchen products, things like that. We're really focused on ergonomics, usability, and problem solving through design on a consumer level that people interact with on a day-to-day basis that hopefully makes their lives a little easier, and they enjoy interacting with the product and having it around their space. So today I'm going to talk about a little bit of a journey through the process of designing a line of eyewear that we did, and really just focusing a little bit more on the maker side of things. So why does design matter? For makers specifically, design is not just about aesthetics, which I love and I wish it was, but it's really about problem solving through design. Right? How does the user interact with it? How does it feel in their hand? What's the experience feel like to them? And then, how we have great ideas that can get stuck without kind of design thinking on what the end user is doing with it. So we want to kind of understand that journey, right? What industrial design is about designing for scale, right? So that we can mass produce a product. It's not just about creating it as a one-off or as like an art piece, but it's more about how do we produce this thing so that it can be sold to the general public. And then industrial design kind of helps bridge the gap between like engineering, like Hextronics, and then how do we build something consumer facing that that the user can interact with using that technology. So our process is very hands-on. We start with the idea, just like any product starts with, right? You have an idea. Then we move into kind of exploring, how we can solve that, or how we can visualize that idea through sketching. In the old days before AI, we used hand sketches, which I love, which is what kind of drew me towards design. In industrial design, in the program that I studied in, our professor was like super old school, and he made us draw for like 6 hours a day. He's like, hey, take this product, draw it every single orientation, understand what the components are of it, right? How do those go together, and then how is that manufactured? So I really drilled in like how to draw a product in 3-dimensional so you can see what that might look like. So we'll help you with the 3D modeling of it, it'll help you with understanding the manufacturability of it, because ultimately we want to produce the thing that we are designing. So here's some just initial kind of chicken scratch sketches that informed some of the form that we had on the first pair of sunglasses that we designed for an eyewear brand. So what we say is no fancy tools needed. There's definitely a lot of ways to go about sketching. You could use AI with prompts on giving you some ideas on that side of things. I love sketching and getting forms out really quickly, and focusing on details, capturing the ideas, and then we can also explore multiple directions really, really quickly. And then we'll move into the prototyping, right? So we're going to do our initial 3D modeling. We want to test for sizing, right? How does it feel in the hand? Is this too big? When you're modeling, it's easy to lose a little bit of focus on the actual dimensions of our products, right? It looks kind of small in the 3D model, but you print it and like, oh shit, this is really, really big. So we print out pretty rapidly. We want to get these forms in our hands quickly. We can test detail quality, things like that. You know, we keep this all in-house. It's affordable, it's quick, it's rapid, and we can make changes really, really quickly. We're testing. That's supposed to move. Doesn't move here. We're jumping into the back and forth in the 3D model, right? We're doing a lot of iterations pretty rapidly until we, you know, get into a form that really feels right. We're documenting pain points, right? Where are weaknesses in the models and things like that. Make improvements fast, rinse and repeat. I'm sure, you know, everybody here does that exact same process. And then we move into the production files and communication with manufacturing. So we're going pretty quickly through this process. An eyewear project like this took about, we were working on 4 pairs at once. Took us about 6 months for all 4, but I would say if we're designing 1 pair of glasses, it would take us, you know, from idea to manufacturable vials in about 2 months, 2+ months, around that time frame, and then launch to market. So I think it's interesting. Speaking about like when you're tinkering with things, when you should start involving like designers in that. If you don't consider yourself a designer, when you should speak to industrial designers, is when you know, you want to kind of figure out a form that feels right for the problem you're solving. You want to start thinking about manufacturability, your IP. You want to start thinking about how you protect that IP if it's something novel and you know, something new to the market. The packaging, the user experience, the storytelling of the item and product. That's kind of our bread and butter. Is kind of that forward-facing side of the design. And that's in a snapshot. That's kind of the process that we use for designing all sorts of things: toys, products, furniture, lighting, things like that. Very, very iterative. We try to move quick if it's not super complex. Yeah, in the snapshot, that's the industrial design process.
How do you go from that to manufacture?
From here?
From the design, the prototyping, to then
so
you're going to get that injection.
Yeah, absolutely. So we start conversations with manufacturing in the kind of the third phase, where we're call it design for manufacturing and communication. Once we have a prototype in hand that we feel really good about, we'll make drawings of that, manufacturing drawings, that we send to our manufacturers for feedback. They'll tell us if the tolerances are okay, right? If it's too small, if some aspects are a little bit too fine, we need to, you know, give a little bit more material in certain areas. Flexibility, right? We're sending what's called design, right? Really detailed drawings of the radiuses of our corners. They're called section views, where you're cutting the product in half so you can see what the material inside is, if it's hollow or if it's a solid body, you know, what those surface curvature is, things like that. And products, multiple part products will have kind of a deck of drawings that we go through, very specifically. And then it's kind of a back and forth conversation until we get samples. That's it. One other. Oh yeah.
Do you work with all kinds of materials? Like, do you work with like foams and like fabrics?
Foams we use predominantly for prototyping, prototyping as well. So instead of like 3D printing a big piece of plastic, we would use foam for that. It's easy to get good curvature and surface finish. We can be. I mean, if you're trying to do something that's like a DIY home kit, right? Like if you want to sell kind of like a kit that people could put together at home. If you think about like cardboard, like cap products, right? Then, you know, we would focus on using cardboard specifically. So I would say yes, if the end product is cardboard. I don't see why not.
I want to chat with you after.
Sure, absolutely.
Where can people find you?
Where can people find me? On the World Wide Web. DBS, we're based in Miami. We have a studio in Miami Beach. The company's DBS Studio. I am a member as well at the Moonlighter Fab Lab. We go there for prototyping. And yeah, dbs.studio is the website. Yeah.
So do you design, when you design for manufacturing, is it what type of manufacturing process?
Mostly, I mean, we're in injection molding, so plastic parts, you know, small to medium-sized products. We're doing some wood products, so it's CNCing and you know, on like if you think of like a baby high chair, things like that on that scale. So I would say wood, plastics, and metals as well. Sit down. Sweet.
Okay. Right.
Awesome.
Thank you. All right. Cool.
Yeah.
Yeah. So, hi everyone. I'm Alie. I'm a native to Miami, born and raised here. Self-taught, electrical, mechanical, kind of whatever engineering. I previously ran a hardware company that made dev boards for the Raspberry Pi, and ran that company for a few years. Sold close to 10,000 of them all over the world. Sold the company, and now I just do like freelance product development and fun LED stuff. So talk now is going to be on the fun LED stuff. So let me see.
Is it a company who would recognize the name?
What?
Is the dev board company one who would recognize the name?
Matrix Labs was the name. It is no longer a band. Yeah.
The name does sound familiar.
But yeah. I also worked at SparkFun after that.
Okay.
Yeah. Anyway, so yeah. So I love pretty lights. One of my favorite DJs, which she was basically my inspiration that has gotten me into like making pretty LED devices. Her name is Rez. I can pull up a picture of her, and you'll kind of understand a little bit here. There's an I don't have internet. Oh, okay, it's fine. So basically, she's an electronics DJ, and she wears LED glasses, just like these actually. Less visible when she wears them, but anyways, in 2019, I got really into her, and I decided to make my own pair of LED glasses. So the first iteration of it was very bare bones. You could see all the wires. It was before I had prescription glasses, so it would just sit right on my face. But it was waterproof, and it ran for years without issues. Most recently, I built these pair, which there they go. So these clip on to my prescription glasses. I don't think I have a picture I could show because there's no internet. But if you want to see me afterwards, these clip onto my prescription glasses. They're waterproof, and they have a LED control board in them. It's an ESP32. A friend of mine makes it. It's a Pixel Blaze. So I don't have internet, so I can't actually show you docs, but I could do this.
There's a guest. The password to the guest Wi-Fi is just Fairchild, no caps.
It's okay. I'm now connected to the Wi-Fi of the boat over here. So this was also something that I did in collaboration with Neil over here, Hedge Clipper. He makes these beautiful laser cut wooden interlocking sculptures. Some of them are buildings, trains, boat, car, future looking things. They're gorgeous. And so we decided to collaborate in the last 3 weeks or something to shove this thing full of LEDs. So over the last 2 weeks, I've spent a bunch of time putting 464 LEDs into this. It's got LEDs in the headlights. It's got LEDs as like side markers. There's LEDs embedded inside the wheel doing this diffusion here. There's some in the engine. If you get closer, there's like some displays inside as well. And all of this is controlled over Wi-Fi via this Pixel Blaze LED controller. So this is the interface right here. My friend makes this. It comes like this, out of the box. So I can go right here and select a different animation. So let's say we want to do glitch bands, or we want to do a kit. Pulse 2D. So the cool thing about this is that it makes doing things with LEDs incredibly easy. Before this, like when I made the first version of my glasses, I was also using like an ESP82666, which is a less powerful microcontroller. And I had a whole interface for it and everything, but that took me so many hours to do. This you could buy for $40 and it works beautifully. But the really cool thing about this is, unlike other LED controllers like WLED, for example, that LED controller, it's a software. You can load it onto your microcontroller. But if you want to change the code for the animations, you have to reflash the entire thing. You have to make it locally, compile it, and then flash your board again. This, on the other hand, can do live. And I'm going to go into the secret menu that none of you should know about, and you definitely didn't see what I typed there. No. So now I'm in the admin menu for this. So I can go right here and see the code that's running this. And you can see on the side, this is a mapping of the LEDs on here. It's a little bit off. Yeah, a little bit off right now. But I spent a bunch of time at, from 6 to 7 in the morning this morning. 4? I don't know. I had 2 hours of sleep. Anyways, so this has like a fully mapped LED. So it knows exactly where all the LEDs are on this device. And then when I run code on it, instead of it being like, okay, the way it thinks about it is like there's 464 LEDs. The first 20 are the back left wheel. And then the next 63 are for the bottom lights, and so on. So rather than writing code to be like, this portion do this portion do that, you can make like shapes in JavaScript. It's all programmed in JavaScript. So if you make a cube or if you do like a sine wave, then you're able to just flow it through the entire thing without having to worry about where exactly all the LEDs are and how they're wired and everything. It just does all of that for you. I can show you some simpler code here. So this is like the intro to Pixel Blaze. It basically just goes down here and does a red, green, and blue. This is like for testing. So it just goes down the position for all of these for the color, and is able to, anything else to this? Oh wow, that's a lot of documentation in there. But yeah, it's basically just able to go down the entire thing. So with, 5, 6 lines of code, you're able to do something on this. Let me show you a more interesting one. And Kit is a good one. Yeah. Yeah, exactly. You can see here the visualization on the side of what's happening. Yeah, so that's basically this. Any questions from anyone?
So was it I2C, like, are they all individually addressable?
Yeah, so all of the LEDs are individually addressable LEDs. They're WS2818s. Some of them are RGBW, like the little marker lights on the top sides of the wheels. Those are RGBW, so they have an extra white LED in addition to the red, green, and blue. But the rest are just red, green, and blue. It's PWM, not I2C. Okay. Yeah.
And as far as the mapping, the visual mapping,
Yeah.
that you have to do
I can
manage?
show you how I do that. Yeah. So you hear the mapper. So this is why it took me so long this morning. There's different ways of doing this. If you have a less complicated layout for the LEDs, then you could go into ChatGPT and tell it, okay, make me a spiral in JavaScript using their documentation, and it'll just do that within 2 minutes, and that'll work. In my case, there are like I did the grunt work of like, okay, these first 20 LEDs are in these coordinates. That's what all of this is. This is all the coordinates for all of the different LEDs throughout this. Going through, I did eventually start using ChatGPT to like increment things because it's mirrored perfectly on each side. That's how I built it to make my life a little bit easier. So yeah. You can see, those are all things, market lights, everything. Yeah, so this is my friend who makes it, electromage.com, I think. It's like a $40 board. Works so easy. I use it in all my projects. There's a tiny one inside of my classes. There's a bigger one in there. If you go to I think it's the Maker Pavilion, the giant tent, there's a standing up laser tube that I made, which was one of the laser light bulbs at Moonlighter for the laser cutters went out, and this is like a $4,000 bulb, but when it's out, it's out. And they were going to throw it away, and I was like, no, give it to me. It's a beautiful piece of glass. So I very carefully threaded LED strips into it. I think there's like 300 LEDs inside of that using the same controller. And the way I was able to do it was with a magnet and a very light string, putting it in there, and then from the outside of the tube, routing the magnet inside all the way up around this 4 foot long, well, tall because it's standing up right now, laser cutter tube. So, yeah.
Can I just say thank you so much for doing this? It was a real privilege to meet you. I think I'm going to deal.
What?
You got a deal.
I mean, this is great. I mean, it's such a beautiful piece. Please go check out Neil's booth. It's over again in the big tent. And he's Hedge Clipper on Instagram. Yeah. And I'm alie.g.g on Instagram. If you want to go see more of my stuff, I'll be here around if you want to see close-ups of it. Yeah, with that, thank you. Jacob?
So my name is Jacob. I'm an engineer of many kinds. And this is a kind of a side project that I've been working on for a new e-bike that I bought. As with any new fast thing, you want to make it faster. And I wanted to do it safely and not die. So in solving the problem for myself and doing the research for, how to make a battery, I'm seeing that this is an undertaking that is not very standardized, and there's a lot of risk involved. There's a reason why there's no kind of standard open source thing going on there. So I want to have a sick e-bike. That involves making a sick battery and a sick motor controller. Probably some other controller maker over there. And then also just want to apply my sensor knowledge to kind of add more throttling or exiting turns and changing how the bike reacts to different motions. So just quick landscape research. The methods that I'm looking at, how people are welding this battery together, are very shoddy, using kind of it's very unstandardized. And at that time, a lot of the imported batteries from China were exploding. And so at that moment, I thought, okay, there's a market need here for some sort of solution. And I could monetize it. And so I could design something extremely quick to do for myself, but seeing the need, I think changing my original design objective helped me to design something for more than myself. So the way that these battery cells, there are many different types of manufacturers, many different kinds of operating firms, many types of voltages. For different biking requirements. If you have a cargo bike, if you have a high-speed bike, you need to design a battery specific to that objective. And so, not only that, but the frame geometries also were very variable. And so that was all pointing to something very modular with repeating parts. And of course, the design had to be manufacturable, assemblable by enthusiasts, would say. And so in the previous talks, we all know about design for manufacturing and assembly, DFMA. And when it comes to open source, particularly in hardware, you need to figure out how to distribute it and then how to make money off that, if that is an objective. So it had to be assembled by novices. So that leads to a repeatable assembly process, and the design itself had to kind of constrain assembly errors. It had to be very obvious. These maker machines at the edge of, everyone has a 3D printer now. Laser cutting is starting to become commoditized, and so right now, those methods are still too variable. 3D printing less so now, but still a diversity of machines at the edge is too variable for this process for a high-risk product. So repeatable manufacture, and so that pushes towards some centralized processes like PCB-way and other kind of centralized manufacturers. And then, with that previous design constraint of modularity and accepting all these different frame sizes, you can leverage quantity volume discounts for manufacturers like that. And then long tail distribution, I can get into design modularity and having one module take the responsibility. I'll get into some more visualizations for that. So for distribution, shipping batteries itself was a liability and expensive as well. So that pressures me to sell a kit where you self-source your batteries and you have all the other components part of the kits. And then for monetization, this is also not fully fleshed out here, but for these centralized manufacturers, they just want referrals and volume being sent to their manufacturing processes. So a lot of them have kind of custom cart links where you can share that cart link and people can have that drop shipped to their house. So I wouldn't need to maintain any inventory, and the distribution of some of the more expensive parts would be handled by that centralized manufacturer. So finding the split of what is to be manufactured and assembled on the edge and what can be distributed from these centralized partners. And so I can go into the battery design itself now. So just kind of working with circles. One of the more fundamental shapes you get is a triangle. You start testing triangles, and let's say I settled on this 60 battery unit because that puts out, let's say, 270 amps at max. Each one supplies, I believe, 12 volts. Sorry, I think. So you can daisy chain each one of these modules to create a 12 volt battery, a 24 volt battery, 36, and I think it's actually 6 volts here. Each cell is around 6 volts. And so this is a 72 volt battery. But if you were to essentially just choose, sorry, I'm not prepared here, but if you were to cut off these top cells here, you're left with a 52 cell, 52 volt battery. You get volume discounts on these. So these are copper bus bars. They are welded to this nickel plate right here, and the shape of this is to minimize internal electrical eddies in the material causing self-heating. And so I wanted a safe bike that was over-engineered for all the safety measures. So these copper bus bars, depending on the cells that you source, can also be changed in their thickness. So that way you can always over-engineer for the current that you're pushing. So this is to minimize current eddies and self-heating, which is a issue in the battery design. This is kind of illustrating the other side. So you can see that in a long tail distribution, I have about 20 of these little squiggles. I have 3 of these, and 3 of these, and 8 of these. So these 4 blue parts are each unique parts that are repeated throughout the battery. And what you're left with when you have, let's say, 20 of these parts, 8 of these, and 3 each of these, you get a distribution that looks like this. So when it comes to optimizing for cost in distribution, this is a kind of a pattern that you want to look for when it comes to a modular design. But then, taking this a step further, that you can even reduce that even further, extract more quantity volume discounts. And so instead of having those 4 unique parts, having a single part that's repeated, and then building up on top of, third dimension. I just have these bus bars, which are a lot easier to manufacture and assemble. So there's that reduces the complexity of the assembly for the user, and it reducing the price of the cost, the cart cost for the copper. Furthermore, like, this is merely an enthusiast project, like a passion project. But if I were to really productionalize this and make it to a long-term business, I would do some optimization in the different parts, which would be closure, the battery cell types, and various other stuff. So the batteries here. This is like a battery control unit, battery management system. So all of these leads are connected to a single cell on the battery. Flows into here for making sure each cell is equal. And then this is the motor controller, which is open sourced, and it is over engineered for how much current I'll be pushing through here. It's kind of a word salad-y presentation, but if you're interested in building an e-bike, I need some push to finish this project too. Yes.
So, one thing that might help is drones have the same issue with needing to push a ton of power to motors. Have you looked at reusing drone ESCs as motor controllers?
The objective for the motor controller is different. So, Kurt can definitely kind of explain this more, but when you're dealing with when you're stopping that bike, I wanted regenerative braking. That was a key component of the motor driver. That it had to accept a huge influx of current from the motor.
And the drone motor controllers I know of, they handle that just by dissipating it through a resistor. So.
Not here.
Yeah, exactly. Yeah.
Well, thank you, Jacob. If anyone wants to see the battery up close, it's right here. Don't touch it.